All right, here's 2017, number 2. This gives us a couple different weak acids. This fulminic acid and isocyanic acid, they are isomers, which means they both have the same elements involved in their structure, but they have slightly different structures. And so A says, this is not an acid-base question, by the way. A says, explain why the diagram on the left is better than the diagram on the right as far as formal charge goes, based on formal charges. And so I did a little pre-work here. Formal charge is the number of valence electrons that particular element has, minus, I don't know if that's how you spell possessed, minus the amount of electrons it possesses in that particular structure. So I'm cheating a little bit here. Hydrogen is the same on both structures. Has 1 valence electron, it possesses half of that shared pair, so possesses 1. The hydrogens both have 0. Nitrogen has 5 valence electrons. Here it's sharing half of those 4 pairs, and so it has +1 on both structures. And then the ones that matter, the ones that differ from one side to the other, are the carbon and the oxygen. So carbon has 4 valence electrons, and we subtract off. Here it's sharing 4 pairs of electrons, so it owns or possesses half of those shared pairs, so it possesses 4 electrons, and that carbon in the first structure has a formal charge of 0. The oxygen in this first structure, oxygen has 6 valence electrons minus the number of electrons that it owns in this structure. It has 2, 4, 6 of its own, plus half of that shared pair is 7, and so oxygen there has a -1 for a formal charge. Good. Know that the entire structure's charge, and here these structures happen to be neutral, so these formal charges in that structure all have to add up to the overall charge. So the +1 and -1 total up to 0. When we look at the carbon on this side, carbon has 4 valence electrons, minus, here it has 2 of its own there, and it's half of each of those share pairs, so there the carbon has a -1 for a formal charge. And the oxygen has 6 valence electrons, it owns 2, 4, and half of each of those, and so it has 0 for a formal charge there. And so when we look at which structure is better, it tells us this structure is better. The reason it's better, and I talk about it in terms of we want the central atoms to be closer to 0. The reason I say that is because in Lewis structures, the central atom has the lowest electronegativity value. Oh, I got these backwards. Carbon there's a -1, sorry. -1 and 0 here. So the central atom is lower in electronegativity when you draw Lewis structures, so this oxygen is going to want that electron or pull that electron harder than that carbon. That's why this is the better structure. So left structure is better. Because carbon is lower in electronegativity than oxygen. So oxygen has the -1 formal charge. That's the right way to write that. That's a lot of work that I did there. I don't know if there's a quicker way to get that done. It's 2 points there. A point for the right formal charges on those structures, and then a point for that explanation on those structures. That's part A. Part B says we can convert one to the other. In this reaction, it gives us the structures of both of those. This is a different structure than the one up top, and it asks us, using the Lewis electron dot diagrams of these guys, determine the delta H value for that HCNO forming HNCO. I wish they didn't make them so close to each other, those structures, but They did. And so here's B. They give us, these are bonds, and so they're bond enthalpies. This is the one place when we talk about Hess's law where we have reactants minus products, or bonds broken minus bonds formed. So I'm going to cheat here. I wrote this out already. So this is the way the delta H works. It is all of those reactant bonds minus the sum of all of those product bonds that are formed. So there are the bonds that you have on the reactant side and product side. It's important that you have double and triple bonds where they're supposed to go. That's a triple bond here, that's a double bond, each of those. And then I plugged in the values straight from the data chart that they gave me. And when you punch those all in the calculator, the delta H for that reaction should equal negative 246. These are all kilojoules per mole of that reaction. That's our delta H in part B, is a negative 246. Taking and plugging those numbers in, reactants minus products from those two structures. Part C says a student claims that delta S for the reaction is close to 0. Explain why the student's claim is accurate. When we look at that equation up here, we have 1 mole of gas here going to 1 mole of gas here. There's no change in the phases, and there's no change in the number of moles of particles. And so therefore there's no change, or approximately no change, in the delta S in the disorder. So delta S is approximately 0 because there is no change in states of matter or phases or in the number of moles from reactants to products. Or if you said we went from 1 mole of gas to having products with 1 mole of gas, that would give you credit as well there on part C. So delta S, the disorder doesn't change, or changes negligibly. Then part D says which species, which of the acid species is present in higher concentration at equilibrium at 298 Kelvin. Justify your answers in terms of thermodynamic favorability and equilibrium constant. Thermodynamic favorability is delta G. Equilibrium constant is our K value, and so we need to address those two things. And so the way I addressed it was this: delta G equals delta H minus T delta S. Because delta S is approximately 0, delta G is approximately equal to delta H. And so delta G would be negative 246 kilojoules per mole. And would be thermodynamically favorable. And then I'm going to come back and address the K value. Delta G equals negative rat link natural log, my N got big there, natural log of K. Therefore, K is greater than 1. And products are favored. What's the question? Let's make sure we answer the question. The question says, Which one's in present in higher concentration? We need to answer the question. I still haven't done it. So the isocyanic acid would be in higher concentration. Be careful with the letters here, right? I would put HNCO. Has greater concentration. Answer the question. Make sure it gets answered somewhere in there. That's part D. Then they have this weird split in the pages on this thing where it says you've got this new equation. Ammonium salt of isocyanic acid, a product of the decomposition of this, gives us an equation, and then it goes on to ask the next question. Nice person, the next question is not really, you don't really need that equation at all in this next question. So part E says you get time versus concentration, you get concentration versus time. This means it's an integrated rate law question, and they give us a graph of that data next to it. It says the student proposes the rate law. Rate equals K times the concentration to the first. Explain how the data support this student's proposed rate law. This student says it's first order. So on E, you're going to say the data shows it's first order because how do we know looking at a set of times in concentration that's first order? It's because the half-life going from 0.1 to 0.05 takes 10 seconds, and then the next 10 seconds we get a consistent half-life. So the concentration is cut in half consistently. So the data shows it's first order because the half-life is consistent. That's it. Constant half-life means that we are dealing with a first order reaction. That's part E. E1. Then E2 comes back and says, using the proposed rate law and the student's results, determine the value of the rate constant. Include units with your answer. You have a wonderful formula on your formula sheet that says the K value is equal to 0.693 divided by the time for one half-life. And so for us, easy enough, we want the K. K equals 0.693, and we can look back up at this guy and figure out the half-life took 10 hours. The unit is hours there. So 0.693 divided by the 10 hours would tell us our K value. Our K value here, you don't even need a calculator, is 0.0693. It's first order, so we take that molarity away, and it's just the number over the time unit, hours. Let's see if I can run that all in hours. Oh, that's terrible. Hours, like that. That's our K value on F. Oh, except it's not F. It's E2. Sorry. And then the last piece for F says the student learns that the decomposition reaction was run in a solution with pH of 13. Briefly describe an experiment including the initial conditions that you would change and the data you would gather to determine whether the rate of the reaction depends on concentration of hydroxide. We would just pick a different concentration of OH and measure how this concentration changes over time. That's it. We would have to keep everything else consistent. I think I cut F off of the one I gave to you because it deals with acid-base stuff. But we'd have to look back at how that concentration affects it at the end. So don't sweat F too much on this problem. We'll see you soon.